Anybody got any questions they'd like to see right off the bat? Otherwise, I have a few things I want to talk about tonight for sure. And I will be putting out a review tonight. I'll put it up, and I'll have the review key up tomorrow. It's on my list of things to do is make the key tonight. The test will be very similar to the review. Mostly because I'm too lazy to change it a lot. Same basic structure, same basic test, that sort of thing. I don't know. Any questions, comments? Carter, you want to say something? Your name's on my screen. Are you saying something?
I'm not saying anything, but hello.
Hey, how's it going? No questions? Anyone? Levi's got a question. No? No? All right. Well, jump in whenever then, I guess. Thing I want to talk about tonight, I kind of just hit this from a little more of a, good Lord, that's an ugly picture.
We have a question, if you don't mind.
Hit me.
So I'm just wondering, like, about the homework. I'm just trying to make sure I'm on the track that you expect us to be on. So we should have done, looks like through chapter 3 as of this week. Is that correct?
Yes.
We do have, so does that mean that?
Wait, let me look at my, where's my thing? You keep talking, I'll keep looking.
Okay. It does look like, and I kind of, I don't know if you remember, but I brought this up in the email at the beginning of the quarter. It looks like because we shifted a week forward, that the last assignment will be due the same week that the final is supposed to be. Does that look right to you? That'd be week 9 some work, and then I guess, so we just done week 4, right? We're on week 4 right now.
Yeah. So we are in week 5? Am I losing my marble?
Technically, it's week 5, yeah, because we lost a week.
Right. Yeah. So, I guess up through chapters. If you have up through section 4, like I'm not going to mark you down if you don't have all of. If you have up through 3 done, and like you don't have part of 4.1 and 4.2 done or something like that, because I think everything I have listed up through week 4 is what I'd like to have done by the midterm. Okay, so that'd be up through 4.2, I guess. If you don't have all that quite finished or whatever, don't worry about it. Just turn that in when it comes in. As far, I'm not really a horrible, awful person when it comes to homework due dates. It's not really that big a deal to me. Quizzes and tests are a big deal. Projects are a big deal, but homework, not that much. So.
Is there, so will we just go from week 5 to week 8 then? Is that what we would do? So do 4.3, 4.4, and then 5.5, and 6.2? And skip week 7?
Well, I'm not going to skip anything. We're just going to compress everything down a little bit.
Gotcha. Okay.
You'll still hit everything. It just, we're going to have to compress everything down a little bit.
Gotcha. Alrighty.
But you're right. You're right. I did not include that in my syllabus. So that's a good point. Well, I think I did, but I didn't. I did take that into account. So we'll probably just end up that week 10 or whatever, the dead week or whatever. Learn some more stuff during that dead week.
Basically. Gotcha. Alrighty. All right. Thanks so much.
Into account.
Okay.
So midterm is going to be on the 13th then?
That's next Wednesday. Yes, sir.
Yeah. Okay.
All righty. Here we go. So a couple things I just want to hit a little more in depth, and that's the idea of expected value. Expected value and variance and / standard deviations. Come on, what's wrong with my computer? Whatever. So they're different things. Obviously, this is one thing, and this is, well, it's 2 different things, but the same basic premise. And so when you're given, for instance, let's just say we have a nice little discrete distribution, whatever it is, and 6, no, that's too much, stupid. 5/10 would work. And 1/10, I guess that would give it to me. Okay. So if I wanted to find the expected value of this, expected value is always the sum of the x's times the p of x's, or if you prefer f of x, your book tends to want to use f of x. Don't really care, where I goes from 1 to n. Okay, these are the x sub i's. Okay, and so, but it's just an x right there. Well, it'd be the x sub I. So the idea here in this case would be simply be this: it'd be 1 times 1/10 plus 2 times 3/10 plus 3 times 5/10 4 times 1/10. Now, that's all fine and good. I mean, anybody can play the game. What does it actually mean? So this is 1/10, 6/10, 15/10, and 4/10. So 19, 25, 26/10, I guess, which is 2.6. What does that represent? Well, expected value is always the long-term average. That's all it ever means. Okay, it's the long-term average. If we did this thing forever and ever and ever and ever and ever and ever and ever, play it again and again and again and again and again forever, that's what we'd expect it to be, long-term average. Okay. Now again, there is no such thing as 2.6, but that's the same reason why you can't get like the average American family has 2.2 children or something, but no one has 2.2 children. People have 2, 3, 1, 9, 7, whatever. My brother has 8. But it averages out. That's what that long-term average is all about. Okay. Something I like to do a lot is I like to do a lot of simulations. So I will share this with you real quick. Should use my other computer. No, I don't care. I'll use this one. All right. So are you sharing, Jay? Jay started to share. Can you see that yet? It's my Excel. Stop sharing. Well, I want you to unpause.
I don't see anything yet.
Come on. There it goes.
There we go.
Nice. Now, all right. So what I'm going to do is I'm going to simulate some data because, well, I can, and it makes me happy. So it's as if I was going to roll a dice or something, and so my outcomes are 1, 2, 3, and 4. Is that right? Wasn't paying attention to myself. Yes. And they are 0.1, 0.3, 0.5, I think, and 0.1. Is that right? Right. Yes. Excellent. Okay, good. So what I'm going to do is I'm going to just basically throw dice a bunch of times. Okay, I'm just going to let them go nuts here. And so random number generation. Again, I could do this. Had I done it with the dice, of course, it'd be 1, 2, 3, 4, 5, 6, and then 1, 6, 1, 6, 1, 6, 1, 6, 1, 6. But I can make up my own thing. So I want there to be, let's say 10 variables. That's going to be 10 columns of data, and I want 1,000. I want 1,000 in each column. So it is going to do that for me, and it's going to pick random numbers based on that distribution right there. So again, picture it's a 4-sided dice, if you will, or if you prefer, there's numbers in a hat, and you're just going to reach in and pull out a number and look at it, write it down, and throw it back in. And there's, if you will, 10 pieces of paper in a hat. 5 of them have the number 3 on them, and 3 of them have the number 2 on them, and so on and so on and so on. Same principle. Boom, there they are. So I just played the game 10,000 times. Okay, draw a number, stick it back in, draw a number, stick it back in, draw a number, stick it back in. Check this out. Equals average of these guys. Whee! I know I could just type it in. It's more fun to be interactive. A little exercise here. Whee! There we go. And look at that. Oh, what? The average from this sample of 10,000 data points, 2.6042. Okay. Now, had I just randomly selected any 5 of them or something out in the middle, I could do this too, right? This is also an average. Are you with me? I can average those guys. Notice that that average is quite skewed because I took a very small sample size. And it was random. I just reached in there and clicked somewhere. I didn't pay attention. A very small sample size. So in statistics, this has applications in a variety of places. But from a cognitive standpoint, I like to think of it this way. Bigger is better when it comes to sample sizes. You can, eventually you get to too much, okay, obviously. But when you want to find out people think about something, going and asking 15 or 20 people, not enough. 1,000 people, it kind of depends on what size town or what size country you're dealing with. You know, did this tomato fertilizer work? I don't know. How many plants did you try it on? 2. What? No, that's not a big enough sample size. And the idea that you can really skew data from a very small sample size is a big deal. 10,000 data points, that is, I think by anybody's estimation, a long-term average, okay? And so that is what we're doing when we play the expected value game, okay? That's one thing I want to kind of just, again, kind of hit home tonight with. If these were dollar bills and there was 10 bills in the hat, so here's my hat, and there's 10 bills in here, there they are. Those are dollar bills, those are bills. I know you can't really tell, but there they are. And you can't see it, I'm not sharing. Damn, I hate this Zoom, it's so stupid. No, you have to stop sharing and then start resharing. Sorry, there it is, there's my hat, you see that? Now you can see my little hat up here, see, and it's got bills in it, you see that? And you're gonna reach in and fish out a bill. And yeah, what would the average payout per draw be? Be $2.60, that's what this means, okay? Now, if you're playing a game, hey, step right up, reach in, grab a bill out of this hat. Well, you're not going to give people $2.60 to play your game, okay? So what are you going to do? What are you going to charge them? What are you going to charge them? I'm going to charge them $2.60, Jay. Really? Because you want to break even? That seems silly. No. What a normal person would do is, listen, no one's going to play your game for the chance to win a whopping, you know, on average, $2.60 a roll, and then you're probably going to charge them $3. No one wants to play this game. So what you do is you shake it up. You make it more interesting. You say, well, let's do this. Look, you can win a $5 bill, and you can win a $10 bill. Oh, that's exciting. And a 20. Oh, or you could win a $500 bill. Whoa, I want to play. And then there's $0 bills too. You're like, what does that mean? It just says, haha, you lose or something, okay? So there are, let's do it, make it nice and easy. 60 of those. Oh, that's cheating. Let's make it 30 of those. And let's make it 20 of those. It's 50, and 20 of those, 70, 30 of those, that's 100. I mean, make it 29 of those. And 1 of those. So if I'm not mistaken, those are each out of 100. Okay. In other words, I have 100 bills or 100 slips of paper in my hat. I'm gonna let people reach in and draw. Okay. Well, what are you gonna charge them to play this game? Okay. They could win $500. Yeah, but you know they're not really paying attention. They could lose, of course. You've suckered them in at this point, right? And so what do you say? Well, first of all, I need to know what I'm going to stand to win, or what I'm going to stand to lose as the guy who's putting this thing on. Because remember, if the customer wins, you, the house, loses, or most likely, if the customer loses, you, the house, wins, right? And so you need to figure that out ahead of time. This is the expected value. This is exactly how it works in Vegas as well, by the way. Every time you play in Vegas, your expected value, your expected value is always negative. However, I get people to play my game because they think, oh, I could win, you know, this much money. I could win this much. Yeah, but you're not going to. But I could. Well, nah, okay, sure. So the average winning here, the average winning per hand on this deal is $12.45. Okay. If you're putting this together and you want people to play your game, what are you going to charge them? You're like, oh, well, I could charge them $20. Well, that's just silly. No one's going to play your game because in essence, then they're going to win $12.45 on average, but they had to pay $20. They're going to lose $7.55 to play your game. And so what we normally do is we make it so that you lose, we bleed you dry slowly, okay? So typically a situation like this is, oh, look at this, we're going to charge you, I don't know, this one seems silly to me, I shouldn't have done it this much, but we're going to charge you $13 or something. Well, look at that, you only lose 55 cents every time you play. Well, I can do that, that's easy, I can win $500. Oh, all right, cool. My favorite is actually Roulette. And I've never actually played the game. I find the rules fascinating for me. If you don't know, there's 1 to 18. There's 1 to 18, 19 to 36, and then 0 and 00 are your numbers. Okay. There's 18 red, 18 black. There's 2 greens. Those are all I really worry about. So let's say that you put your money on 17. Let's go, lucky 17. You have a 1 in 38 chance of winning. You have a 37 and 38 chance of winning, a big fat 0. Okay. What happens if you win on this? Well, I happen to know that the rules state that you will win $35 plus your $1 bet. So $36. Cool. So 36 times 1 over 38 plus 0, obviously, minus the $1 it cost you to play, because that's what you bet. And so it ends up being 36 out of 38 minus 1, which turns out to be a nickel. Okay. And it turns out that it doesn't matter, that you will lose, in essence, a nickel every time you play this game. Okay. A roulette. Now, at no point did you ever lose a nickel. No, in fact, you won $36 or you won 0. Those are your 2 options. But on average, it comes out to be that price. Okay. So again, I'm going to simulate a few rounds of this. Now, it's pretty straightforward that when you do this, it seems obvious to, I think, to most people that if you play this for 3 or 4 games, you could either win really big because you win one time and finish, like, oh, I finished really well, or you could have lost, a few more than normal, and it obviously you'd come in, behind. The idea being is that when you're doing these, obviously simulation wise, if you won like one more time than you were supposed to, it can kind of throw your numbers off. Yeah. Let's change these to these. And voila, boom, there they are. So again, look at that. I won on my second play. I bet on 17. I won on the second roll. Look at that. But then look how, I'm going to go down this column. Look how many more it took on that column before I won again. Holy crap, did I ever win again? Whoa. Oh, I'm getting killed. Look at that first column. Holy crap, it took me to 161 to win again. Dude, I am way behind. But then over here in these other columns, you're like, but I see a bunch of 36s, like right there. Boom, boom. Right, one right after the other in column F. And so it's important that you keep it in mind that it is right there, I was killing it over here too. Look at that, row I, I'm just killing it. But remember that that's how life goes frequently too, by the way. Like someone's just take it in the shorts and someone else is like being the lucky one here, right? So the average of these guys, so I'm just going to type it in this time. I'm too lazy to do it. J1000. So the average per roll, or the average winnings, the average of all those was, actually I did that wrong. Hang on, let me do that differently. I'll do something a little different here. So equals sums, what I want to do. A1 colon J1000. Look at that. I made $9,200. That's awesome, Jay. Not really, because to win $9,200, I played 10,000 times. So I had to bet $10,000. Oh, well, I ended up in the hole $784. Wait a minute now. How much is that per game? I don't know. Equals that divided by 10,000. So in essence, I was losing 7.8 cents per game that I played. Now, you're like, I thought it was supposed to be 5 cents. Yes, theoretically, it's supposed to be 5 cents per roll. It's actually 5.2 cents per every time you play the game and you bet on a single number. what is this telling me? This is telling me that the theoretical and the actual, of course, will always be different. Now, again, 10,000, how close to infinity is that? Not that close to infinity in the real grand scheme of things, okay? So that's going to happen from time to time. Now, the reason I really like roulette, I just like the way that it works out. It doesn't matter what you bet on. The expected value is the same every time, okay? And the expected value is always negative a nickel. If you, for a $1 bet, it's always that. And so the idea is like, oh, I only lost a nickel. Well, I'm only losing a nickel. Well, I'm only losing a nickel, and we'll bleed you dry. But remember, every game in Vegas, the lottery, everything, always negative. That's how the place looks opulent. Okay. If you were to bet on red, well, there's 18 out of them are 30 out of 38 of them are red. That means the other 20 out of 38 are not red. You win 0 for that. And I just happen to know, because I studied this a little bit, you win your money back plus the dollar. You win $1 plus whatever you bet, plus the dollar that you bet. By the way, if you'd made a $5 bet, you'd win $5 plus your $5 back. Okay. And so, but we're just going to say it's a $1 bet. So we're going to win our dollar back plus another dollar. So that's 2 times 18 out of 38 plus 0 minus 1. And again, you will lose a nickel on average every time you play. Okay, now that's great. I like talking about roulette. I like roulette in theory. Never played it, but how does that affect my daily life? Well, statistically speaking, you have a certain chance of dying, and you take out an insurance policy. Let's say you take out a $100,000 life insurance policy today. Okay, and so here's the game. If you die, you win $100,000. If you don't die, you don't win the $100,000. Oh, that sucks. So wait, what? Yeah, so it's a little weird. So if you have a 1 in 10,000 chance of dying today, you have this chance of not dying today. That's cool. So your expected value of betting on your dying is 100,000, which would be your winnings, times this, plus 0. What do we call that? It's not really a bet. What do we call that when it's insurance? Come on. Starts with a P, people. Premium, yes? Minus the premium. This is your bet, if you will. And then this is equal to, your actual expected value over here. Okay, that's exactly what it's supposed to be. And it will be negative. You will expect to lose money on this deal. That's great. So this is why insurance companies hire actuaries. They want to know what we should charge people for premiums so that we, the insurance company, get a certain amount of money per policy so that we stay in business. Okay. So for instance, the insurance company says, listen, for this guy, because he's 25 years old and in perfect health, we would like to make $30 off him. Okay. I just made that up. So don't worry about it too much. And by the way, I only talk about what are my term life policies is all I talk about. When you get into when you get to health insurance, car insurance, any other kind of insurance, oh, I got in a car wreck today. Oh, that's cool. You gonna claim it? No, it's gonna cost too much. Oh, so actuaries have to take into account not just the fact that you get in a wreck, it's the probability you got in a wreck and you will claim it. You see that? So they're always dealing with conditional probabilities. And so what is it conditioned on typically? Well, how bad the wreck is, how fancy the car they are, how broke they are right now. Is it drivable? There's a variety of reasons why they would choose to claim it or not claim it. Okay, so, oh, it's a fender bender. No, I'm broke, so I'm not going to claim it. There's a variety of reasons. So they have to take all that into account when they figure out the probabilities. It's not as easy as you're living or dying with the term policy here. Okay, but so 1 in 10,000 times 100,000 should give you $10. So if you solve for the premium, I'm going to have to charge this guy a $40 premium for this $100,000 life insurance policy, which isn't unrealistic for someone who's like 25 years old and in perfect health. Okay, so that guy, very little chance of dropping dead. Okay, and so the insurance company, as a result, is going to be taking his $40 every month or whatever it is, and saying, "Listen, we're going to sit on this money and we're just going to keep sitting on this money. And where's that going? Well, we're going to use it to pay out, you know, whatever the people that do die, and we're going to have enough in our coffers based on this probability. Okay. My dad used to sell life insurance policies, and one of his best friends is this guy. Is about, he's maybe 5'8" and about 400 pounds. He's a big, horribly overweight. And so my dad, when the guy came to buy a policy, my dad's like, "Oh, brother." And I said, "What?" He's like, "Well, they're going to charge him a fortune for a life insurance policy." Turns out that they wouldn't even insure him. Like, he was going to die, like, you know, today. And so the company can't get enough money out of him, probabilistically speaking. They wouldn't even take the bet. Okay. And so keep that in mind, that once you have these scenarios in the mind, that's the whole premise of pre-existing conditions and things like this, is you're so much more likely to have to be able to use it again. Then obviously that's why the companies need to charge you to make some more money on the deal. It's all about probability and statistics on it, in that game. Likewise, when Hurricane Katrina hit, you know, people will insure their houses and for hurricane damage and all this. You expect as the insurance company to pay out on several hundred policies a year easily, okay? But that's spread out over the entire season. That's not several thousand spread out in over one, you know, weekend period or whatever, where you just got hammered. And that's why those insurance companies took it really hard in those time frames, is because they were not prepared to pay out that much. Again, it's all about probability. The guys, the actuaries, sit down and figure out, this is about how much we're going to need to have in stock. We charge everybody accordingly, and, you know, hopefully not a ton of them, you know, we don't have a rash of payouts, because if that happens, if the insurance company gets quote unquote unlucky, and they have to pay out a bunch, then they can really be hurting. But that's the whole process of how actuaries do their thing. It's all about expected values. The tricky part is coming up with these numbers here, the probability of you dying and living and stuff. And if I'd have known that was a real thing where you could sit in a back room with a giant monitor and nothing but spreadsheets all day long, wow, that'd have been fun. But, you know, life goes on. It sounds like a very fun job to me, but it's not something I actually ever got into. So I enjoy the idea of it, though. That's how they work. Now back to, why did I get away from that? So back to the idea of expected value. Oh, no, I'm just going to steal this one. I was just going to steal it again because it's a pretty one. Once you're here, oh, fart. Cool. If I want to find the variance, which is something else I always want to do, how spread out is my data, it is always equal to the expected value of x squared minus the expected value of x squared. Okay. Well, we already know this guy. This guy here is 2.6. Okay, we just found that a few minutes ago. Now, how are we going to find the expected value of x squared? Listen, anytime you find the expected value, it is always the sum, in this case, because it's a discrete distribution of that thing, so x squared, times the p of x. That's it. That's all there is to it. And so it's going to be 1 squared times 0.1 plus 2 squared, 0.3, 3 squared, 0.5, 4 squared, 0.1, 7.4. Is that, I don't know, hope that's right. Oops. 0.64. Wow. Look at that. Listen, if this ever comes out to be negative, you screwed up. Can't happen, all right? Because sigma squared, obviously it's a squared number, and I'm going to have to square root it in a minute. But it's a distance, friends. It's a distance. You cannot have a negative distance, okay? Ferris Bueller's Day Off. You cannot back the miles off the car, all right? The distance is always positive, okay? And so if this ever comes out negative, you screwed up. Go figure out what you did wrong. And then, of course, the square root of that should be 0.8, and that is the standard deviation. Okay. So that's a big deal. That should be something that should stick in your head forever, I hope. If someone ever asked you, hey, I'd like to know what is the expected value of 2x, Jay? Well, I don't know. How would I find it? Well, didn't you say it was 2x times p of x? I did say that, yeah. And so wouldn't it be then 2 times 0.1 plus 2 times 2, so 4. 4 times 0.3 plus 2 times 3 is 6 times 0.5, and then 2 times 4 is 8 times 0.1. Well, each of those has a factor of 2 now. Well, if I factor that 2 out, what I'd end up with is this. But wait a minute, this right here is the expected value. That's right. Oh, wait. So the expected value of 2x is just 2 times the expected value of x. That's right. That's exactly right. Okay. However, don't be this guy. The expected value of x squared is not equal to the expected value of x squared. Okay. In fact, it's greater than. Okay. But don't be that guy. But if you're multiplying by a constant, then yeah, pull the constant out front. It's 2 times the expected value of x. Piece of cake. Okay. What if you did something like, oh, I don't know, the expected value of x minus 1? I don't know. I don't know. But you do. So if you did this, well, x minus 1 would be, geez, I can do this math in my head. What's my first number? My first number is 1. 1 minus 1 is 0. Plus 2 minus 1 is 1. 3 minus 1 is 2. 4 minus 1 is 3. And that comes out to be 3 plus 2 times 0.5 over here. 0.3 is, no way now, no way. It's 1.6. Well, what is that? Well, 1.6 is the expected value of x minus 1. And so whenever you have this situation, this guy right here, you can rewrite that as the expected value of x minus the expected value of 1. What is the expected value of 1? Wait a minute. 1 is just 1, Jay. That's right. So the expected value of x minus 1. Oops, it's not equals 1. Minus 1. That's it. Okay. So those are big deals that we'll use going forward. It's important that you're confident with that. It's important that you understand that going forward. Okay, because when you're doing this, all you're doing is you're taking the averages of numbers. In the case of this guy, you're making the numbers 2 times bigger. So what's your average going to be? Twice as big. Hey, you're taking the average of 1 less than the number you currently had. So what should that do to my average? It should make it one less than it was previously. That's right. That's right. And so that's the kind of the game that's going to be happening there. When you think about that, I think that helps to sell it in my head a little bit when I do that. What would happen if you multiplied by 2? What would happen to the variance? Ooh, let's find that out. That's a good question. So remember, the variance was this guy, but be careful on that, minus this guy. That's just how we find variance. But I want to know the variance of 2x. I'll do that down here in little parentheses. So it's the expected value of 2x squared. So oops, that's supposed to be on the inside. Sorry about that. Like that, okay? Because it's no longer x that we're squaring, it's 2x that we're squaring, minus the expected value of 2x squared. Interesting. So what's going to happen here? Well, when you do this, you're going to get the expected value of 4x squared minus the expected value of 2x, sorry, of 2x squared. Well, what's the expected value of 2x? Well, it's 2 times the expected value of x. So this is 4 expected values of x squared. And then this guy over here, well, wait a minute. You said you could pull these guys out front. I did say that. So that's 4 expected value of x squared. And they both have a 4 in common. So if you pull that 4 out, you will see it's this minus this. But wait a minute, Jay. This right here is the variance of just x. That's right. So when I do this, if I want the variance of 2x, it is 4 times the variance of just plain old x. And that will always be true. Always, 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 always. So when you multiply by k, it's going to be k squared times your old your old variance rather. Okay, it'll always be that way. Because what are you doing when you multiply by 2? You're taking the numbers which were 1, 2, 3, and 4, and you're making them go 1, 4, 9, and 16 over there somewhere. What have you done to the variance? How spread out it is. You've made it a lot more spread out by timesing them all by 2. So you've made them a lot further apart, and it's not going to be just twice the standard deviation. It's going to be a lot more of the standard deviation. In fact, it's going to be k squared more. What would happen to how spread out they are if you just did this? What would of x minus 1, what would that be? Well, think about this. If I just took the numbers that are like 1, 2, 3, and 4, and I shifted them here, how did I affect how spread out they were? Well, I didn't. All right, I didn't spread them out. I didn't change how they're spread out. I just shifted them all down a little bit. I affected their average, but I didn't affect how spread out they are. Okay, so this case is going to be equal to this guy. Okay, and so whenever you add a constant to your x, or add or subtract a constant to your x, whenever you do that, you don't affect the spread of your data. Therefore, you don't affect the variation or the standard deviation of your data at all, because you didn't spread it out anymore. Okay, when you multiply it by something, you make it that multiple k squared times bigger variation. That's a big deal. I cannot really overestimate that or overemphasize how important that is. That's something that I want you to take away, and that's always true. Okay, I don't care if it's a continuous distribution or if it's a discrete distribution like the ones we've been looking at. They will be exactly the same. Okay. If you want expected value, well, first of all, let's do this. So here's my f of x, and I'm just going to make it do this, something like x from 0 to 2. Let's put a big fat A in front of that or something, so that, because I want to make it work. Okay, 0 elsewhere. Okay. Well, first and foremost, for this to be a PDF, this thing has to integrate to 1 over its interval. I'm just not feeling it today, so integrate 3 plus x comma 0 comma 2. It's 8. Oh, that's handy. All right, right on. So 8a it needs to equal 1 because it has to equal 1. So a is equal to 1/8. Which means if I just come back here and I'll put that over 8, I guess. Now I have myself a PDF, and isn't that swell? If you were to look at Desmos, maybe. Desmos. There we go. Boom, 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 boom. X plus 3. What are you doing? Divided by 8. Awesome. There it is. And we want to go from 0 Nope, I forgot my squiggly brackets. Pardon me, I'm just a rookie here running this thing. Hey, there we go. Cool. That red line is my PDF. Okay. That is all it is. And at 0 before then, it jumps up and takes off, and off she goes. Okay, that's my probability over there. Now, when I do this, let's think about this for a minute. If I were to integrate this guy, okay, what do I end up with? Well, I end up with, that's x. What are you doing? Where did this come from? Where's my numbers? Oh, there's my numbers. Let's go back over. Well, I can do this in my head, can't I? Yes, x squared divided by 2 plus 3x divided by 8. Nice. Nice. That looks good. And so this guy right here would be my CDF. Like so. And don't forget your squiggly brackets, dummy. What the heck? There we go. Cool. Oh, not to 8, to 1. Nope. Try 3. Ooh, there you go. Good. And something's a little screwy there. What's wrong with this? There's a little thing wrong with this picture here. Do you see it? Do you see it? Do you see it? Do you see it? There's something a little bit wrong with that picture. Let's go do some calculus here. See if I do this right this time. Oops, come back. What is going on? Somewhere. Why don't you share? Ah. I don't want to quit Zoom. I just want to get into Zoom. Okay. Oh, it's over here now. There we go. Share. So let's go back and do this guy here, shall we? So it's going to be 3x plus x squared over 2 over 8 from 0 to 3. Let's see if I did something wrong. Let's use my calculator wrong. That'd be funny if I did. I did. Damn it. I didn't integrate correctly. That's embarrassing. Well, actually, I was fine. See right here, I put 0 to 2. It was actually 0 to 3. No, it was 0 to 2. 0 to 2. Then I did it right? Hot dang, I did it right. I just can't run a calculator. No, it's right over here. Here's my problem. Sorry, I'm getting dizzy too. Here we go. I just need to change this to a 2, you big dope. Nice. That's more better. The problem I was having was that the blue line should have stopped at 1. Are you with me right there? And it didn't. It kept going higher than 1. That's a problem. Because when you do this, what are you saying? You are saying that that my probability starts at 0 and it increases, and it increases until you get to 1 over here. Okay, that's my CDF. Now, what is the average value across that line? Okay, let's go see if we can figure that out, and then we'll figure out what exactly that means. So over here, we have our PDF. That's lovely. And if I wanted the expected value of this PDF, it would simply be the integral from 0 to 2 of x times my PDF. And so 1/8, that's 3x plus x squared. And so that'd be, I don't know, 3x squared over 2 plus x cubed over 3 all over 8, I guess, from 0 to 2. And so it's 4 divided by 2 is 2 times 3 is 6. It's 8/3 over 8. It's 13/12. Interesting. 13/12 is 13 divided by 12 is 1.083. Repeating. So if you go look at your Desmos, you don't see your work doing right now. You can see it now, can you? I hope. All right. So if you come back to this Desmos, okay, the average of this red line right here, the average of this red. So when I look at this guy right here, we wanted to figure out what is the expected value across that range of this x plus 3 over x is. And the average of that should have been, what did I say? Whatever I said it was, 1.083. That's the average value of that guy, okay? And it's a little goofy there. Pardon me while I type this into my calculator. I'm just gonna do it on my calculator. You're not missing anything at home. 1 divided by 8 times the integral of 3x squared x squared 2. No, 1312. Okay. So all it's telling us is that that's our average value across that region. That's all it wants us to know. And that the idea of that is, so it's once again, you're just finding the, hey, what is the average across that particular value? Remember, those values are probabilities we're seeing. And so you're looking for what is the average across this particular value, across this interval area. Again, that's if I can find the right picture. We're looking at this red line right here, this x plus 3/8, all right, that guy right there. Find the average across that value. So that's x equals 1.38, or just a little over 1. That's where the average value happens, okay? So remember, you're getting values of x's, and they can happen anywhere between 0 and 2. And what you're doing when you're using this equation right here, this x plus 3 over 8, is you're finding the probability of being in any particular value. But because it's discrete, you cannot actually get, or it's because it's not discrete, because it's continuous rather, the probability of any one of those x values is 0. But what we're saying is, if you took them all and you averaged them up, what would the average x value be? The average x value would be 1.083, or 13/3 if you prefer. 13/12 rather. X equals 13/12. What just happened? I don't know. Okay, that value right there, where the green line intersects the red line, okay, that is the x that is the average value across that line. That's all it's saying to us. Okay, it's hard to remember sometimes because people want to look at the y values and they're like, why isn't that working? It looks weird because the y equals 1 is clear up here. That's nice. We weren't talking about the ones. We're talking about the average x value that you would see across this interval, and it's just a hair bigger than 1. Okay. Ditto, if you wanted to find the expected value of the variance. Oops, I got to share screens with you again. If you want to find the variance of this guy, and again, I think it's important just to feel confident in this in yourselves, that how this works. If you want to find the variance, remember it is just the expected value of x squared minus the expected value of x squared. So all I have to do is the expected value of x squared is the integral from 0 to of x squared times 3 plus x. And then we're off to the races. So 1/8. It's going to be, well, I can't do it in my head. 3x squared plus x cubed dx. So x cubed plus x to the 4 over 4, 0 to 2. Well, that's nice. So you get 1/8, 8 plus 16 over 4 is 4. That's 12, so 12/8, which is 1.5. So you're going to end up with 1.5 minus 13/12 squared. And so if you do that, you will find that, oh, for Pete's sakes, 1.5 minus 13/12 squared, you will find that's 0.326 or thereabouts. And that would be the variance for this particular problem, okay? They all work exactly the same way. So I really want that to be a big deal in your head going forward. What if I have a joint PDF? Okay, well, what about it? Well, my joint PDF is XY. Oh, okay, cool. Well, if that is your joint PDF, and if that truly was a workable PDF, and you wanted to find the expected value of X, I can't do this without doing it. So 0 to 1, Except that's going to be a quarter. It's going to be a half, and a half is a quarter. So I guess a quarter maybe. Let's double check if that's right. The integral of the integral x, y, x. Oh, sorry, I gotta have a 4 up front. That's no problem. Sorry, gotta put a 4 up front because it adds a quarter in, so I need to have a 4 up front. There we go. Sorry. So this is my PDF, 0 elsewhere. That's nice. All right, so what would the expected value of x be? I don't know. Wouldn't it just be x times the PDF? That's right. Integrated over both intervals, yeah? That's it. And what about the expected value of y? That's a great question. Yeah, just like that. Or dy dx that turns you on. Remember, because this is a rectangle, I can integrate in any order. If x dependent on y or y dependent on x, that's freaking me out. My camera turned on. Then you'd have to be careful of that, of course. How would I find the expected value of x squared? You put an x squared right there is the only difference. Ooh, but if I wanted to find the expected value of x times y, then you'd put that right, in place of the y. Yeah, exactly. That's all there is to this stuff. There's not a lot to it, and I don't want people getting all weirded out about it. I remember when I first learned this back, and I'm like, oh my God, there's so much to do. There really isn't. You put what you're trying to find the expected value of right there, and then you integrate, okay? The only tricky part would be is if y depended on x somehow, you'd have to do some funking around with the limits of integration. That's all you'd have to mess with, okay? But other than that, not that big a deal. So when you watch the variance piece again, and you look at some of the expected value stuff again, pay attention to that. Also, if you want the marginal of x, remember the marginal of x, what do? Well, you integrate out the y's. But notice if you do that, okay, I did not introduce another value of y right here. You see the difference? I want the marginal. I'll use some other terminology here. It's like g of x. This is the marginal distribution of x. So what I want to do, I want to get rid of my y's. Okay, so integrate them out. Okay, and same way. So notice up here we're doing expected value of x. We're doing a double integral on this guy. All right, but down here I want to leave my x's in. I want my x's to still change. I just want to get rid of the y's. They're not important to me for whatever reason. I want to know what's going on with my x's. Maybe that's the only part that I care about. Okay. Those are the big things that I think that you should, I hope, start to get in your heads, and not like, I don't want you, I mean, granted, you can use open notes. I don't care about that. But what I don't want you going is, oh my God, there's so much to this. There really isn't. And I don't mean to like say it. People sometimes say that I say it like, oh, this is totally easy. I don't mean like that. What I mean is it's the same process over and over and over and over and over again. Okay. And once you've established the process, it's just a matter of, well, what am I looking for this time? Am I looking for the expected value of x? Am I looking for the expected value of y? What am I doing? Am I going for my variance? What piece am I looking for? But all of those pieces come out to be more or less the same. If we were in class today, and if we were like in a classroom today, we'd be breaking out some Excel. We'd be doing some more random number generations and discovering some things. To me, I just think that's the fun part. I enjoy the algebra now. I remember when I was a kid, I'd watch the professor do it. I go, what happened? Because I like algebra probably more than the next guy. Well, I know I do. But even then, sometimes you're like, okay, cool. What did that buy me? Versus if I can simulate it and see, in fact, what's happening, like I did over here on the Excel page, and I can see, look, I just randomly generated numbers. That's all I did, and then boom, it matches up with what I wanted to see. So here's, for instance, is this particular first distribution. Oh, and by the way, I didn't do this. Equals. Check this out. This will be fun for you. Equals var p. Yes. Oh, where did it go? Oh no, I didn't type it in. Let's try this again. Equals. That's an E. There you go. Var p parentheses. Nope. Equals vape, man. Cool. There we go. Nice. And then A1 colon. Okay, come on, it's a colon, dude. Colon. What is the point of having a tablet if you can't just type it in? J 1000. Nice. Enter. 0.64, baby. What did we say should have been on that problem? Do you remember? I do. I think it was. Is that right?
I think you got it right.
Oh, somewhere. I'm sure it was 0.64 anyways, but I feel good about myself now. Oh, it's here somewhere. I don't know. Anyway, 0.64.
I remember saying it.
Anyway, the idea is when you look at that, the reason I like to do that as in class is because I think it's easier when you as a student can visualize what's happening and see how it goes. To me, that's the one thing there. Yeah, of course you can use calculators to do the integrals. Yes, for sure. This is not Calc 2, okay? Don't care at all. I still want to see the integrals written out, so I want to see integral from 0 to 1. I want to see what you're doing. But yeah, by all means, have the calculator do the integrals for you. Here's the thing. You could spend hours doing a problem in this class. Like you could spend my entire, let's say we're in class, like in the summertime, this class goes for 4 hours in class. But let's say that I did that and I went for the full 4 hours in class. I could do sometimes, like you could, if you wanted to, you could just get lost on like 5 problems doing the double integrals and all this stuff. And then of course you'd make some mistakes too along the way. And what was the point of that? I don't know. So I definitely use calculators. If you're happy and you like you like the TI-89s or you're an Inspire guy, go for it. If you like to use Wolfram, you're welcome to use that too. I don't care. I don't have any dog in the fight on that deal. You know, whatever makes you happy. Yeah, so that's kind of where we're going on that. Again, I just think that there's so much in when we're doing these guys. There's so much of this expected value stuff that people get so weirded out about. They don't understand what's going on, and they think it's so much different, and it's just not. It's the same basic premise again and again and again. And if you can kind of get yourself convinced of that, I think you'll find the rest of the class goes a lot smoother in that regard. After we get done with we'll continue out the rest of the book talking about continuous variables. We're going to do some more after the test with some discrete distributions. There's about 6, is it 6? I think it's 6 discrete distributions that we'll look at. And there'll be a homework assignment on those, which is kind of fun. And then we'll get into some more continuous ones like the normal distribution and, for instance, the T, the F, chi-squares. And these other distributions, the idea being with them is that once you understand them, those ones, the continuous ones and most of the discrete ones have functions built into the calculators and to Excel because that's what they've been, you use them all the time. We use those ones all the time. And so you'll still be doing the same concepts, but once you understand what a CDF means, it's the concept of it's the probabilities up to that value, whether it's an integral or a sum up to that value, then you know what the calculator is asking for. Then you can use the calculator or the computer correctly. It'll be doing it behind the scenes. Now, on these problems over here, I just got done integrating. I was doing all those by hand. That's nice. All the real continuous distributions like the normal, the exponential, the gamma, the chi-square, F, T, none of those have an integral in closed form. None of them do. So if you were going to do them, you'd have to do them numerically. So the computer has built-in functionality for that. Behind the scenes, it's doing an integral behind the scenes. And you're happily ignorant. You aren't, because you know what it's talking about. But when I teach a stats 243 class, or 244, those kids are just like, oh yeah, here I'm doing it. Oh yeah, I'm using the normal distribution on the calculator. The answer is this. I'm like, but they have no idea what they're actually finding. It's just finding the area under a curve. It's doing an integral from here to there. None. And so you guys will understand that better. that helps you, I think, more than anything else, is looking into, well, what's the calculator wanting me to do? It'll be a 3-hour test, and then there'll be a, so it'll be 3 hours to work on it, and then another half an hour to get it uploaded. So 3.5 hours total, so there's not a whole lot of whatever. Do it on a sheet of paper, and then take a picture of it and send it back to me. As I say, show me the integrals that you're doing, but by all means do it on a calculator. If you use Excel for anything, send that as well. That's fine. Forward that along as well. But that's kind of the game. Any other questions there? I think it's funny, Levi, you're always on my screen. Next
I got a
homework,
question.
next set of homework due next week. I think that's right. Yeah. Should be due next week. Yep.
I was wondering about on the test, what type of format you're doing for that? Are we gonna print it off, work on it, and then scan it back in, or?
Yeah, just like that.
Okay.
Yeah, as far as the graded stuff, I will have the pivot table graded. As far as the homework goes, I don't really look over those very thoroughly, because I'll look at some of them, but I won't look at them all like question by question, make sure they're perfect. But I will look over the pivot table. Those will all be graded before the midterm for sure, and make some comments on them. Yeah. So the test, anyway, don't worry about showing up late. I actually skipped class last week. Yeah, I'll look over see if you're showing enough work, that sort of thing. Sure. So I'll when I do the midterm, when I do the key, I post it tomorrow. You'll kind of see the kind of amount of work probably that I'll show. That's kind of my plan, I guess. I think it covers up through section 4.2, but I wouldn't swear to that. I just printed off an old test from a previous term. I'm just going to make the key for it tonight. I kind of look through and kind of tell you what it goes over when I get ready to send it out, and then kind of prepare from there, I guess. Okay. Anyone else? No? Any questions on homework? We feel okay about homework?
I think so. When is the Dropbox open for that?
For the second
Or
set?
whatever the folder to put that in. Is that open yet?
I don't remember. I'll go look real quick. I thought I opened one of these boxes the other day, but I might have done for the other class. Yeah, I don't see it. I'll put it up. Week 1 and week 2 homework is there. Week 1 and week 2 homework is there, but I don't have the rest of it. All right, yeah, I'll get that put up tonight, right after the meeting. I'll do it before I go to bed or anything here. I thought you just made an assignment for it. I did make an assignment for it, but I don't see it on there, Robert. Do you? I did, or I thought I did, but I didn't. That's what I did for week 1 and week 2, but I don't see it on here for the second week. So I'll just throw it on there. I'll leave it up here in a second. I'll do it after I get done talking to you guys. Any other questions? No, maybe. All righty. Well, I guess that's all you got. That's all I got. Yeah, so 3 hours, and it'll be approximately what's on this test. I mean, I won't change the format a great deal from what I have on this other assignment or whatever, this other test, this review test.
So
Okay.
how many questions should we expect?
I have it over here. Oh shoot, do I have it over here? Just a second. Oh, I printed it off at work today. I think I left it over there. But here's the electronic one. Come on. Yep. And no, oh shoot. And let's see. That no, not the final, you dummy. Midterm, summer. All right, so it looks like there are on this test 23 problems. Yeah, 23 problems or thereabouts. Yeah, something like that.
Okay, thank you.
Yep.
Should we expect multiple choice from the book?
No.
Like anything out of our reading or anything? Okay.
No, it'll be. I don't really do a lot of multiple guess stuff. It's on this test. There's not a lot. Next test, there's going to be somewhere you kind of have to critically think about a few things and then say it's most like this or most like that. So it'll be questions like, well, like next term, it'll be things like we're discussing some of the discrete distributions like binomial, multinomial, some of those. And so I'll give you an example and you'll try to say, well, that one, it probably most closely represents this distribution or most closely represents that distribution by thinking it through and then explaining it. That's about it. The rest of it is just going to be, here's a math problem, read it, story problem, and do the math problem and solve what you asked to solve for. It won't be a multiple guess. Ah. Okay. All right. Well, I'll get going on this tonight. I'll get it. Actually, I'll probably get it scanned. No, I won't. I'll have to go get it first. Well, I'll get it scanned in the morning for sure. But I'll send it out. I'll actually send it out right as soon as I get done here. I'll post it. I'll send it out. I guess I won't post it. I'll just send it out, and then I'll make the key in the morning. Okay. All righty, y'all. Well, have a good night.
Thank you. You too.
All right.